viewers, welcome to my channel. In this tutorial we are continuing our series geometric progression. That just ended, we did with the sum of finite geometric progression, and the sum of the n terms, where the common ratio is what? Either less than 1 or more than 1. That is when the sequence given to you have a finite terms, that is the last term being known. There are instances whereby the series is endless, that is, it is moving into infinity. How do we find the sum? Because the last element will not be known in order to use in calculation. So that is where this formula we are going to deal with come into play. If you are new, consider to subscribe, share and like this video. Now, if we want to take a series, which you know is the addition of the sequence of a GP to be A plus AR as first term, this will be the third term, the fourth term, then we continue to move up to infinity, meaning the series continues. Now, if you are asked to find the sum of all of them, you know there are missing term here. In the previous one, even though there's a missing term, we'll still have a last term, so we can easily find the missing term. But here, I can continue to end up to the 12th term and still have several number of terms that is unknown. That is where the infinity or infinite sequence come into play. So under this, we are going to consider where the common ratio is going to be less than 1, meaning it should be fraction, which is a proper fraction. You know, if we have this, then we can say the GP is going to be convergent. Now, if I want to find the number of terms present, we know is Sn equals to first term 1 minus r exponent n all over 1 minus what? R. That is the case where the common ratio is less than 1 for the n terms for finite. Now, if you want to do this, we can do this in two ways. In order to manipulate this formula to suit what we are looking for, we can see that this can multiply to give us a minus ar exponent n all over 1 minus r. We know under fraction, when this is having two terms, we can divide each of the term by the denominator. So this can also be a over 1 minus r, then minus ar exponent n over 1 minus what? R. We can say this is the same as this. From here, we can take it as this. Now, since we are saying that the common ratio is going to be a fraction, then if I have 1 over 2, then another 1 over 2, another 1 over 2, if I keep on multiplying this, the value will continue to be less or approaching 0. The moment we continue multiplying, you know, this is going to be 0.5. This will multiply to give you 1 over 4. That's also going to be less than 0.5. So the more you continue adding, as in this case, the r is raised to the power n, meaning the r is multiplying certain number of times. So when the n is increasing, then your r will be what? Decreasing. Meaning moving, if this is moving closer to infinity, that is a larger number, then your common ratio will also be what? Moving closer to 0. That is, we are approaching what? 0. So if we are seeing that, it means if this is increasing and this is approaching 0, it means the numerator is going to be 0. Then 0 over any number will still give us 0. It means we can take care of this to move away. Or we still employ the principle of limit. The limit, we can find the limit of this as in limit of Sn as what? Our n approaches what? Infinity. And that could also be given as limit as n approaches infinity of a over 1 minus r minus a 1 minus r. And we know that as this is approaching infinity, if I put infinity here, it's going to make the whole of this to become what? 0. So if the whole of this becomes 0, then this is going to be Sn equals to a over 1 minus what? R, in the case where the R is less than what? 1. Good. So the formula we are looking for is the sum of infinity GP, or the sum to infinity of a geometric progression, is given as A, which is the common first term over 1 minus what? R. And bear in mind that the R will always be less than what? 1, in order to have a convergent. For you to be able to have the sum, when it is divergent, it means you cannot be able to find the sum of the infinity. Meaning this R is going to be greater than what? 1. Very nice. So it's not all of them that we can find solution. It is only in the convergence that we can find the solution to the sum. Alright, so let's take a question to see how we can put this into use. Okay, find the sum to infinity of the GP, first term negative 5 over 4, 5 over 16, negative 5 over 64, and 5 over what? 256, and the series continues, the sequence continues. So first of all, we know that our first term is going to be minus 5 over 4. What will be our common ratio is going to be this, as in 5 over 16 divided by negative 5 over 4. And if we invert this, so if we invert this, it becomes 16 times negative 4 over 5, where this will cancel to go a 4. So minus 1 over 4 will be our common ratio. So we know the common ratio, we know the first term. Those are the only two things that we need. So our sum of all the terms there is going to be negative 5 over 4 over 1 minus common ratio negative 1 over 4. This is what we are having. So let's maintain the 5 over 4. Then let's do our division. This is going to be addition. So this is the same as 4 over 4. Then this is going to be 1 over 4. And 4 over 4, we have the same denominator, we add the top. And that will give us 5 over what? 4. Per inversion, this become minus 5 over 4 times, flip the fraction, 4 over 5. This will cancel, this will cancel. So we'll be left with minus 1. Meaning this sequence, if you continue generating the sequence, adding all of them to infinity, your answer will approach what? Negative 1. So this is how we find the sum to infinity of a GP. I believe the concept is clear. It's a little bit different from the sum of the n term of a GP. So the moment the GP continues, then we are asked to find the sum of all the terms, then this formula come handy. I believe you follow the concept. Thank you so much for watching. Make sure you share this video with somebody who may need it on your contact list. Subscribe if you are new, like, and leave a comment. Bye-bye.